So share a little bit. What's the problem? So is everything okay?
Yeah, it's not in presentation mode, but we see it.
It's not in presentation mode.
No.
And now? Is it in presentation mode?
Still not.
Still not? That's a problem. It's strange. Why? Okay. Can I show it this way?
Yeah. If you don't manage, yes.
Okay. I'm sorry for inconvenience.
No problem.
Good morning to everybody. My name is Timur Nizamov. I am a, a postdoc of Laboratory of Multifunctional Magnetic Nanomaterials, Russian Institute of NUST-MISIS. And my topic is seed-mediated synthesis of zinc, manganese, cobalt, iron ferrites using a leaf growth concept in polyol media. Well, magnetic nanoparticles are widely used in biomedicine, especially ferrites. They're used in magnetic hyperthermia for cancer treatment, for magnetic separation, for drug delivery, because they have high surface area. They're used in MRI contrasting and in magnetic targeting, and they're universal. They're very useful. And their main benefit, is that it's possible to remotely control by applying external magnetic field. So you can trigger some internal processes in tissues, in cells, like heating or mechanical action, some mechanical effects, or another no way.
Sorry, Timur.
Yes,
the presentation is not scrolling.
it's not scrolling.
Yeah. So in the chat they say to press F5 to get into presentation mode, and maybe you're
Yes,
sharing the wrong screen.
I hope. I hope no. Now.
Okay, now it's scrolling.
It's scrolling. It's
yes.
Third. Yeah.
But now you're in. Yeah. Okay. Now you're on the third slide, but we see the first one. Okay. They tell us to try to reshare again from the beginning. Could you try to? Okay, thank you. So, okay, now it's in presenter mode.
And so is it okay now?
No, it's in presenter mode. We see also the notes and the other. I think you're sharing the wrong screen again.
Okay, let me try it again. Or is it better now?
Is it the same as before?
And now? Is it?
Now it's slide 3, but it's not in presentation mode.
I don't know what's wrong.
Maybe you can try one last time to reshare everything and see if it's going right this time.
Is it scrolling?
No, it's on slide
On
number
the-
1. Okay, now it's number 3.
But not in a full screen mode.
No, not yet.
So should I leave it in this? In non-full screen mode, or what? What do you think is better? Maybe
Okay,
like
if you come back to the presenter, okay, this
like this.
this is better, yeah.
Sorry. So the way how the nanoparticles will interact with the tissue, with the cells, depends on their magnetic properties. And the magnetic properties depends on the size of nanoparticles, their structure, what metals they consist of, and how they arrange among each other. And that's why the synthesis of magnetic nanoparticles of the necessary size and structure and their magnetic properties is important. But the current methods of chemical synthesis of magnetic nanoparticles, they are like the most popular are like co-precipitation, hydrothermal, thermal decomposition, and polyol methods. And most of them have their like pluses, minuses, drawbacks. Like the simplest one, co-precipitation is easy to carry out, but it's hard to control nanoparticle size. In our case, we choose the last polyol method, and it's pretty easy to carry out. It gives a good control of size, and what's important, it gives a chemically active surface. The nanoparticles, after the synthesis, they're not stabilized with a strong stabilizer. That's why after that it's possible to modify the nanoparticles and give them necessary properties. But this approach has one important drawback. It's hard to synthesize nanoparticles more than 8, maybe 10 nanometers in size. And that's why we decided to, here's a description of polyol synthesis of magnetic nanoparticles. And to fix this drawback with the size, we decided to realize the concept of leaf growth. The main point of this leaf growth concept is to separate the process of nucleation of nanoparticles from the growth. How can it be realized? The best way is to synthesize separately in one specific condition, in specific conditions, the seeds, initial seeds, and then use them in different conditions to obtain the final nanoparticles. And we realized that this concept. How we realized it? First of all, we synthesized by typical polyol synthesis seeds, and then we use them as as the seeds to grow the final nanoparticles via injection of precursors of metals into the solution, into the seed solution. And by this approach, we synthesize the nanoparticles like of twice size bigger. And the optimal conditions of this approach is like medium, like 3-ethylene glycol, while the temperature is lower than at the synthesis of initial seeds. It's like 225 degrees. And we tested different injection rates, and we realized that the higher injection rate, the more side processes of side nucleation happens, and the lower injection rate, the nanoparticles are more like monocrystalline in structure, and by repeating those processes step by step, it's possible to obtain nanoparticles with a wide range, up like maybe 80 nanometers in size, or 90 nanometers up to 100. After that, this approach we use this approach to obtain cobalt ferrite nanoparticles of different stoichiometry, like with a stoichiometry of x equal 0, x is 0.5, x is 1. And a wider range of nanoparticles was obtained. Like we can compare like initial seeds with the size less than 8 nanometers, then first series with the size up to 15 nanometers, and the second series with the size up to 35, 40 nanometers. And magnetic properties of the nanoparticles was examined, and we saw that the nanoparticles half doped cobalt ferrite showed extraordinarily high coercivity, even higher than the pure cobalt ferrite nanoparticles. After that, this approach was used to obtain magnesium and zinc ferrites, and moreover, this approach was used to obtain core shell structures, like with the iron oxide core and cobalt ferrite shell, and three different nanoparticles of iron oxide of three different sites was covered with the cobalt ferrite shell, and hyperthermia measurement revealed that the maximum SLP was 778, up to 778. Then we also carry out the synthesis of nanochains, magnetic nanochains, like in situ in the reaction media, or after the synthesis by application of a constant magnetic field. In both ways, then magnetic nanochains are formed. It happens because there is no strong surfactant on the surface of the nanoparticles, and any kind of slight like external influence effect, like magnetic effect, can cause the arrangement. And the ease of the magnetic ease of surface modification and the absence of the strong stabilizers enables to carry out pegylation, like we did in this publication. We covered nanoparticles with a redox responsible organic shell of PEG, and also we obtained magnetic electric composites by covering the magnetic shell with a barium titanate magnetic core with a barium titanate shell. So here are the conclusions. Should I read it, or it's not necessary? So I think I finished.
Okay, thank you very much for your talk. Is there maybe time for one quick question from the audience?